Most of our day-to-day algebra functions are continuous everywhere. Or, if they're not defined everywhere, they're continuous everywhere they're defined. So we've already said that polynomials are continuous everywhere. We didn't use the word continuous, of course, but we said that if we have a polynomial and we want to compute its limit as x approaches c, we can just stick c into the polynomial. And that we now know is the definition of continuity. When we talk about a function being continuous, we mean it's continuous everywhere if we don't specify a point. Rational functions are continuous where they are defined. So, I mean, the rational function x squared over x minus 2. Well, this can hardly be continuous at 2, can it? One of the requirements of continuity is that the function has to be defined at the point that question, and R of 2 is not defined. So it's not continuous at 2, but it's continuous everywhere else. The fancy way of getting this idea across is saying that it's continuous on its domain. And again, this is not new. We already know that rational functions are continuous on their domain. We, of course, did not use that phrase, but we did say that the limit as x approaches c of r of x equals r of c as long as R of C is defined, as long as it doesn't give us a division by 0 error. Power functions are also continuous on their domain. So f of x equals x to the negative second is continuous whenever it's defined. If I want to know the limit as x approaches 3 of x to the negative second, well, as long as 3 to the negative second is defined, this is the limit. That's how continuity works. And since 3 to the negative second is defined, it's 1/9, this limit is true. The limit as x approaches 3 of x to the negative second is 3 to the negative second, which is 1/9. This textbook treats exponentials and logarithms separately in a later section. It maybe doesn't assume that every student in this class remembers exponentials or logarithms, but I'll just write it down for completeness that exponential and logarithmic functions are continuous on their domains. Finally, functions built out of continuous functions are continuous. If f of x and g of x are continuous on their domains, so are f plus g, f minus g, f times g, f divided by g, be a little careful. F divided by g might have a different domain than f and g do, but this is continuous on that domain. And also f composed with g. So in practice, the vast majority of functions we work with in our day-to-day lives are continuous on their domains.